How do ADCs manage quantization, error, and noise? Imagine trying to capture a smooth flowing river with a camera that only takes snapshots at specific intervals. The images you get are close but not perfect. That's similar to what happens in an analog to digital converter. These devices turn continuous signals into digital numbers, but they can't do it perfectly. The difference between the real signal and the digital approximation is called quantization error. It's like the small step you miss when climbing stairs. To manage this error, one common approach is to increase the resolution of the ADC. Resolution is measured in bits, and more bits mean more levels to representing the signal. For example, a 16-bit ADC can distinguish between 65,536 different levels, while an 8-bit ADC only has 156 levels. The more levels, the smaller each step, and the less the quantization error. This makes the digital output more accurate and improves the signal-to-quantization noise ratio, which tells us how clear the signal is compared to the noise. Another trick is called dithering. Think of it as adding a tiny bit of random noise to the input signal before conversion. This might sound counterintuitive, but it actually helps. Dithering spreads out the quantization error evenly, turning it into a kind of white noise that's less noticeable and less likely to cause distortion. It's like shaking a jar to even out the contents, making the overall picture clearer. Oversampling is also used to reduce noise. Instead of sampling just at the Nyquist rate, which is twice the highest frequency in the signal, the ADC takes many more samples. These extra samples spread the quantization noise over a wider frequency range. Then, digital filters and decimation techniques remove the unwanted noise from the band of interest, making the signal cleaner. Some ADCs, like sigma-delta converters, use noise shaping to push the quantization noise out of the signal band altogether, further boosting accuracy. Good circuit design and calibration are essential too. Engineers carefully select components and fine-tune the system to minimize other sources of noise and nonlinearity. Calibration corrects small errors in offset and gain, making the digital output more faithful to the original signal. Designing ADCs to be monotonic is another way to keep errors in check. Monotonic ADCs ensure that as the input voltage increases, the digital output always increases or stays the same. This prevents sudden jumps that could worsen quantization effects. In real-world applications like sensor data collection, audio recording, or instrumentation, managing quantization error and noise is vital. Engineers choose the right resolution, use dithering, oversampling, and calibration to get the best possible digital representation of the analog signal. In summary, ADCs handle quantization error and noise by increasing the number of bits, adding small amounts of noise intentionally, sampling at higher rates, shaping noise digitally, and carefully designing and calibrating their circuits. These steps help produce clearer, more accurate digital signals from the analog world.